Good afternoon, everyone. Today I'm very excited to tell you our system that can track mobile users' behaviors just using the light around us. This is a joint work with Professor Chang Liu and Professor Xia Zhou. The ability to know what we do and how we behave is of great importance. It can help us to continuously monitor our health condition, detect early symptoms of disease, and interact with many objects around us. However, the existing methods all have fundamental limitations. So for example, for wearable devices, the user has to consistently wear the devices, and not to mention that it is pain to charge the devices every day. For camera-based method, the privacy concern is a big issue because the raw camera data consists of millions of pixels. And recent work looked into the use of the ambient radio signal for sensing. However, the electromagnetic interference is a big issue, especially in some places like hospital or airplane. Also, the sensing capability for such system is limited, and the existing method can only classify some predefined user gestures or just track a single user body part. We take a different approach, and we want to leverage the ubiquitous light around us to sense our body gestures. Our early work has shown the feasibility for such light-based sensing. And the key idea is to leverage some low-resolution shadow maps on the floor to infer the corresponding body gestures. The result is promising. However, given the system setup, there are three key limitations. First, the system relies on hundreds of photodiodes on the floor to capture the shadow. And deploying this many photodiodes on the floor is not easy. Second, the system assumes the user is standing at a fixed location with non-user orientation. And finally, the user is the only blocking object in the system. And it can now deal with other blocking objects, such as furniture. And here, we present Starlight to address all these limitations. Starlight consists of 20 LED panels on the ceiling and just 20 photodiodes on the floor. In Starlight, the user can freely walk in the room and perform arbitrary gestures. The system can track a mobile user and reconstruct the corresponding body gestures in real time in the 3D space. So now let me show you how we design Starlight. And one of the key features for Starlight is that we only deploy a few sensors in the environment. Starlight made it happen by leveraging the fact that we are already surrounded by many LEDs, and many of them are LED panels. Each LED panel consists of tens or even hundreds of LEDs. So if the photodiode can differentiate the light rays from all of the LEDs, we already have many light rays to analysis and detect how our body parts block the light rays. So it is possible to just deploy a few sensors in the environment to infer the corresponding body gestures. However, to build such a system, we face three main challenges. First of all, we have many LEDs on the ceiling. It is challenging to differentiate the light rays from all of the LEDs. And second, we only have a few sensors on the floor. Their placement is another challenge because the furniture can block some light rays from the LEDs. And we need to carefully place the sensors on the floor to capture maximum information. And finally, the user can move around in the room. The uncertainty of the user location and user orientation significantly increase the search space. So we need an efficient algorithm to track a mobile user in real time. And next, I'm going to show you three key design components to address these challenges. Well, to deal with the first challenge, we designed a time-based light beacon. So to differentiate the light rays from all of the LEDs, a simple method is to assign unique flashing frequencies to each of the LEDs. However, challenge comes when we have a large number of LEDs. And here, we did a simple experiment with various number of LEDs. So the x-axis shows the time in milliseconds, and y-axis shows the photodells readings. As we can see, when the number of LEDs increases, the variance of photodells readings significantly drops. And if we project the signal to the frequency domain, we're going to get a similar result. Here, the x-axis shows the LED flashing frequencies in kilohertz, and y-axis shows the frequency power after doing FFT. So it is obvious that when the number of LEDs increases, the magnitude of each frequency power peak significantly drops. So it becomes hard to differentiate the light rays from all of the LEDs, even in the frequency domain. So now you may wonder why it is happening. Well, first, the flashing frequency range is limited by hardware and our system latency requirement. And given the LED flashing frequency range, the more frequencies, the smaller the interval between adjacent rising and falling edges. So, for example, if we had two LEDs and each of them flash at the different frequencies, the combined signal will be something like this. And if we have 16 LEDs, we're going to get this combined signal. And we can see that with more LEDs, the interval between the rising and falling edges significantly drops. So if we keep adding more LEDs, the photo does it work? Can anyone hear me? Okay. So if we keep adding more LEDs, the photodells may not be able to detect the small interval at some point. This misdetection will introduce errors in the frequency domain. So in Starlight, to support a large number of LEDs, we decrease the number of flashing frequencies by reusing them over time. So here we first divide the LEDs into groups. And at different time slots, we just let a specific group of LEDs transmit a light beacon, while all the other LEDs flash at the same base frequency. In this example, we have two groups of LEDs, and we use different colors to represent the LED flashing frequencies. So at different time slots, we just let one group of LEDs flash at a different frequency, while all the other LEDs flash at the same base frequency. So here we can see that we just use two light beacon frequencies to differentiate the four LEDs. And we can combine the beacon frequency and the beacon time slot to identify an LED. To deal with the second challenge, we designed a sensor placement algorithm to optimize the sensor location. Well, each LED has a viewing angle. And as we can see, it can only see a limited 3D space in the room, and we mark it as the blue regions in the figure. And due to the impact of furniture and walls, if we place the sensor at a certain location, it can only see a limited 3D space within the viewing angle. So for the sensing purpose, we need to maximize the aggregated blue region in the room to optimize the sensor location. And it turns out that the problem is equivalent to a maximum site coverage problem, and is monatomic and submodular. We then use an efficient greedy algorithm to find suboptimal solution with a constant bound to the optimal solution. And finally, to deal with the user mobility challenge, we extract two coarse features from an aggregated blockage map to reduce the search space. So at a high level, to track a mobile user, we aggregate all of the light blockage information together to search for the best fit skeleton. And in this example, we aggregate all of the block rays together to find the minimum distance between all of the block rays and the inferred user skeleton. However, for a mobile user, the uncertainty of the user location and user orientation significantly increase the search space, which prevent the system from being a real-time system. And next, I'm going to show you how we extract the two features. And here we leverage a horizontal plane at the height of the user's waist. We then compute the intersection point between the planes and all the blocked rays. By aggregating all of the intersection points together, we can get this aggregated blockage map. And this blockage map contains some cross body features. So for example, the ellipse here shows the user's body section, and the center of the ellipse shows the cross-user location. The two minor axes of the ellipse shows the two user potential orientation. And by leveraging the user's moving trajectory, we can further decrease the search space to track a mobile user. Now let's move on to the system evaluation. And the video shows the 4 main procedures to build Starlight. We built 20 LED panels, and we first solder all of the electronic components on a PCB board, and we assemble the LEDs, the control board, and the power supplies on the LED panels. We finally put everything up on the ceiling and debug the circuit. The whole process just takes a graduate student's 20 hours. Starlight consists of 20 LED panels on the ceiling and just 20 photodiodes on the floor. We then asked 10 participants to perform arbitrary gestures at various locations in the room. We then use a Connect sensor to get the ground truth data. Well, we understand that the Connect sensor may not be as accurate as many dedicated motion capture systems, such as Vicon. But we found out that within a certain working space, the reconstruction error for Connect sensor is negligible. Also, to set up a Vicon in the room, we just don't have enough space to make it up. The figure shows the overall reconstruction accuracy. The x-axis shows the 5 key upper body joints, and the y-axis shows the angular errors in degree, which is a standard metric to evaluate a motion capture system. Overall, Starlight achieves 14 mean angular errors for the 5 upper body joints. And we can see that the performance for the album joint is worse than the other 3. It is because the user's lower arm is the smallest body segment, and given the LED interval on the ceiling, the system may not be able to detect the small lower arm movement. We also did a couple of micro benchmark experiments. And here we first take a look at the system latency. The x-axis shows the 2 main components in the Starlight, and y-axis shows the corresponding processing time in milliseconds. Since the 2 parts run in parallel, the system latency only depends on the slower component. So overall, Starlight can produce at least 40 poster inferences per second. We also measure the localization error, and to get the ground truth data, we let each user wear a laser pen, and we manually label the ground truth data afterward. The x-axis shows the user ID, and y-axis shows the localization errors in centimeters. As we can see, Starlight can achieve 4 centimeters indoor localization, meaning indoor localization errors, which is good enough to precisely track a mobile user. And given the possible offset for the use of the laser pen, we also compare the moving trajectory for Starlight with that of Connect system. And we found that the mean trajectory deviation between the 2 systems is just 2 centimeters. We finally want to know what the furniture impact to the system. And here, we set up 3 different furniture layouts in a lab environment, and the 3 plots on the top shows the furniture layout and the corresponding sensor placement. As we can see, the performance difference between the 3 layouts is quite close. And we found out that the performance for the 3rd layout is slightly better than the other 2. Well, if you take a look at the furniture layout here, all the furniture is placed on the side of the room. It gives our sensor placement algorithm more free space to find a suboptimal solution. Now let's conclude the talk with a couple of potential applications and future work. Starlight can enable many applications in HCI and behavior monitoring. By just simply walking in a room and perform arbitrary gestures, without using any cameras or on-body devices. If we can get continuous user body movement data, we can learn some patterns of the user's behavior and find a correlation of the user behavior. By using these patterns and correlations, we can detect some early symptoms of disease, such as Parkinson's disease. Moving forward, we want to track multiple users. However, in this scenario, the blockage map can be overlapped, and it is hard to differentiate them. So we intend to take a look at some machine learning algorithms and some other sensing techniques to tackle the problem. So thank you for patience.